Okay, looks like most people are in now, so we'll get started. So thanks all for coming along. For those who are new, welcome. This is the Newcastle University Whole Energy Systems interest group. We're delighted today to have our first international speaker all the way from across the pond. We've got Kyri Baker, who'll be talking about building operations. So just by way of brief introduction, so since August 2017, Dr. Baker's been an assistant professor at UC Boulder in the Civil, Environmental and Architectural Engineering Department. She also holds a courtesy appointment at the Department of Electrical, Computer and Energy Engineering and a joint appointment at the National Renewable Energy Laboratory, NREL. She's a fellow of the Renewable and Sustainable Energy Institute, a joint institute between CU Boulder and NREL. Previously, Dr. Baker was a research engineer at the Power Systems Engineering Center at NREL and a postdoctoral researcher in the Residential Buildings Group at NREL. She received her PhD in Electrical and Computer Engineering from Carnegie Mellon University in Pittsburgh in December 2014. She is interested in how advanced controls and optimization methods can help integrate renewables, facilitate building to grid interactions, and foster efficient operation of our future smart grids and smart cities. So I think Kyri's talk will be about half an hour, maybe 40 minutes. If you have any burning questions as we going along, you can sort of raise your hand and we'll try and answer those as we're going, or we'll also have time for questions at the end. So Kyri, whenever you're ready.
Okay, thank you. My name's pronounced Kyri, by the way.
I'm very sorry, Kyri Baker.
No, it's okay. I get it almost every day. All right, thank you for having me. I'm really excited to give my, I think, first international talk of the year, maybe second. So I'll be talking about some of the research I did it while I was at NREL and also now that I'm doing at CU Boulder. So we already went through this bio. I'd spent 2.5 years at the National Renewable Energy Laboratory, which is a US Department of Energy funded facility that only performs renewable energy and renewable sustainability research, unlike all of our other national labs in the US. If you haven't heard of architectural engineering before, I had not before I joined the department. It's a focus on building systems. So it's not architecture, it's designing and engineering the systems that go into buildings, like mechanical systems, electrical systems, structural systems. And they're starting to expand this program to be more inclusive of the grid, because as you probably know, the line between buildings and the grid is starting to blur. And so that's why I was hired, I guess. I would just like to thank my group, which is called the Griffin Lab at CU Boulder. The work I would have done without these students is much, much smaller. In particular, the two students whose work I'm going to be talking about today are Caitlin, who's graduating today, actually, and Ash, who just started this year. But the rest of my lab tackles these problems of grid optimization, building to grid integration, renewable energy, everything like that. Okay, so I'm assuming most of you know this, but just for some of you who might be new to the field, the future power grid is going to hopefully be cleaner, a lot more of intermittent non-dispatchable generation. Dispatchable meaning we can control the output, non-dispatchable meaning something like solar or wind where we can't just crank a dial and have it produce more electricity or produce more energy. There are new electricity prices. We don't just have a flat rate in many parts of the US anymore. We have time of use pricing where the electricity price changes throughout the day. In some areas of the US, we actually have real-time pricing at the residential level, which is pretty interesting. And there's a lot of new load patterns. So more people are buying plug-in EVs, more people are buying electronic devices, more people are working from home. The traditional, peak in the morning, peak in the evening demand curve, we're starting to see more variations on that. When the grid was built, there weren't a lot of considerations for how much things would change, especially in 2020, the grid is experiencing all sorts of new problems and new challenges. So how do we get around the lack of infrastructure? It's not just simply ensuring generation equals demand, it's also ensuring that all of these line constraints, all of these transformer constraints, congestion, all these problems are addressed at the same time in this huge complex system. So at the high voltage level, we have the transmission grid, and that's why the talk is called Thermostat to Transmission, because in order to achieve the best and most cohesive operation of the grid, I argue that all of these pieces need to be working seamlessly together. So traditionally, we had large power plants up here, power flew downstream to consumers. Now we're adding generation closer to loads, so more and more people are having rooftop solar, there's more distributed generation. There might be an electric vehicle that plugs in here. These energy systems are becoming more and more integrated. So it's not just building owners and building designers ignoring the grid, acting like it's an infinite source of power. And it's not like grid operators and grid planners are completely ignoring buildings anymore. So one good example of that is we had a bunch of blackouts in California in August this year because of this huge heat wave. There was a couple generators that were down in California. And so there was a lot of people that experienced power outages. And what they decided to do was they just texted people, they posted on Twitter, can you turn up your thermostat to 78 degrees Fahrenheit? So a bunch of people did that, and it helped the grid avoid another blackout. So demand response, building to grid, all of this is becoming more important from both the transmission side and the user side. Okay, so I'm going to be talking about 3 topics today, kind of going up from the building level and abstracting upstream. So from an individual building level, I'll talk about a project with a smart home that I started at NREL and continued on to CU Boulder. Oh yeah, it's called CU Boulder because in the US, UC is taken by the University of California system. So that's why the University of Colorado uses CU Boulder, just to avoid confusion. Then we're going to go up to the neighborhood level. So how can we design prices for a community of houses? And then I'll talk about a project that just started last month, which is more at the city or district level, which is the joint design and operation of microgrid and district energy systems. Okay, so let's look at a single building first. Let's just look at inside this one building, single thermostat, couple of people living in there. Can a single building impact the grid? No, of course it can. Of course it can. So a building's electricity consumption in the US is, and this is an outdated number, it's probably even higher now, is about 75% of the electricity generated goes to just residential and commercial buildings. So I'm not talking about industrial facilities, factories, manufacturing, stuff like that. The transportation slice has grown, as well as the building site has slightly grown. It's kind of been flat, but it's slightly grown. But buildings can have such a huge impact on the grid. 75% of that electricity is going to those buildings. So this has been realized since the 1960s, actually, in the US. Demand response has been around for a very, very long time. Traditionally, it was the utility calling up a consumer and asking them to shut off something in their factory. Now it's getting more automatic. You might have heard of automated demand response or automatic demand response. Generally, there's 2 categories of demand response. There's time-based, which is the utility provides some incentive that varies with time. That's sent to you or sent to your smart meter, and you can decide whether or not to manually respond or to automatically program your smart thermostat to respond. There's incentive-based, which is more of an irregular thing. So we have something in the Colorado utility that I belong to called the Savers switch. This is a physical switch that goes on my AC compressor. And when the utility is experiencing periods of high demand, they can just shut mine off. And I get paid for this, of course. There's also demand side bidding. So you can either through an aggregator or if you're a larger building, actually bid into markets. There was a Federal Energy Regulatory Commission order passed this year, a few months ago, that now allows distributed energy resources to bid into markets. So that's very exciting and could revolutionize a lot of what I'm talking about. There's also other types of markets that you can participate in, and it varies by region. Okay, so the goal with this project, which is now roughly completed, it's in people's homes now, a couple unlucky people, is we wanted to create a home energy management system that addresses 4 different objectives. We wanted to save the user money. We wanted to keep them comfortable. We wanted to help the environment by using power when generation is clean. And we want to help keep the grid stable. So avoiding those blackouts that we talked about earlier. And this was a joint project when I worked at NREL and then when I continued on at CU Boulder, between the Department of Energy, the Bonneville Power Administration, Bosch, and Colorado State University. So it was a really comprehensive effort to make this cyber secure home energy management system. Okay, so it's called foresee. And the reason it's called foresee is because it uses model predictive control to foresee into the future. And in the objective function, it addresses the four C's: cost, carbon, convenience, and comfort. And so here's what the user interface looks like. It's a mock-up here, but we actually made a product that looks like this. So it allows a consumer to look at the state of the various appliances in their house, assuming that all these appliances can talk to each other and that have communication capabilities. When we actually tested this, there was a little bit of hacking, you could say, that had to go into making the water heater communicate and with all the other devices. There are efforts being made for communication standards and ways for devices to do this. But if you go to the store, at least here, like there's a store called Best Buy where you buy appliances and tech stuff. They have ovens that have Wi-Fi now. So I don't think this is too far out from assuming that all of your devices are going to be connected. So you get to control your thermostat. You get to see how much your solar panels are producing. You get to see how your carbon footprint has decreased depending on how flexible you were with your goals in your home. And this won an R&D 100 award, which honors the 100 most innovative technologies of the year. So that was very exciting. We worked with behavioral scientists at Colorado State University to design these surveys that people understood, that the average person could take the survey and those preferences would be translated into mathematical weights in the objective function of the optimization. If you ask a consumer, what's your objective function, so I can program it into the MPC, nobody has an idea what objective function is. Nobody understands, even I don't understand what I kind of understand what an objective function is, but it's much easier for people to understand, is it okay for me to have a cold shower? Is it okay for me to be slightly colder than I want or slightly warmer than I want? So there's a lot of different survey techniques for this. One you might have heard of is analytical hierarchy process. It's a way for people to rate whether or not choice A or choice B is better. And at the end, it spits out these weights that can be used in an optimization. So the researchers at Colorado State University developed a new type of survey. And essentially, you provide the people taking the survey with different options. So here's a list of options. You move these up or move these down depending on how important they are to you. So for me, I would probably put shower temperature at the top, air temperature next to it. Dishes, clothes, not too important. Lowering my environmental impact, maybe move that up. Saving money, I could keep that at the bottom. So depending on where people rank these, it translates into a convex function that can be easily optimized by foresee. And there's different functions for air temperature, shower temperature, when you want your dishes washed, stuff like that. A lot of these devices obviously have inherent limitations, like you can't just tell the dishes to fly into the dishwasher and wash themselves. So it does require some human intervention. But the main things here were water temperature and air temperature, which are also two of the big power consumers in a house. Okay, before this was deployed in those unlucky people's homes, we tested it in the lab at NREL. Here's a picture of the lab. You can see some of the washer and dryer here, the plug-in EV. Here's a smart fridge. I feel really lucky to have been able to work in this lab because I got access to a lot of these products that hadn't come out yet, or I got to see, the smart home of the future. So over here, we have a bunch of different loads that we considered. This is just to say you could consider an EV charger. We didn't in the demonstration. We had the Bosch team work on the cybersecurity layer. So it would be not only uncomfortable, but potentially dangerous if somebody was allowed to remotely control the devices in your house. And then we had a large home battery that helped us shift these loads while keeping the user comfortable. And then this screen is just what the user sees. They have no idea what's going on here. Okay, so into the guts of this thing. So the core of it is this model predictive controller. And if you're not familiar with model predictive control, it has models of the devices it's optimizing over. So we had simplified models of the house that we learned over time. We had simplified models of the water heater. We optimize over multiple time steps into the future using forecasts of temperature, forecasts of load. Depending on what goes on in this block, we then send set points or control actions to the physical system. And then there's going to be some mismatch between what our linearized model predicted and what the physical system actually did. So then we send back these measurements and update the model, rinse, repeat, etc. The system identification block just helped us learn better home models and better models of the appliances over time. Okay, so what my student worked on at CU Boulder was, instead of just using forecasts, can we actually incorporate the shape of the uncertainty? So the distribution of the random variables for outdoor temperature, for like solar irradiance, stuff like that. So my group does a lot of work in chance constrained optimization, and that just is a type of optimization that deals with uncertainty, and it wraps constraints in what's called a chance constraint. So if we look at this here, the utility sends some signal to your home. It says, please reduce your load by 3.4 kilowatt hours. So here, the B util is that 3.4 kilowatt hours. Here's how much energy you were predicted to use from the MPC controller. Here's the amount of energy you're actually going to use. And we want to ensure that this is at least 3.4 kilowatts of reduction with a high probability. So there's many ways of dealing with chance constraints. If this random variable, whichever it is, the predicted power, the grid power, is normally distributed, you can actually boil this down into an analytical form that's exact. If it's not normally distributed, there's a lot of other techniques you can do to reduce this chance constraint to something that we can deal with in the optimization. If you were to try to solve an optimization with the probability of a constraint, you would find quickly that you need some way to reduce it to an actual equation, because probability of isn't something you can take derivatives of, for instance, and do gradient descent on. So this ensured that the grid receives what it requested with a high probability, but it's not going to over constrain the home to really try to meet this if it's really, really expensive, for example. So we applied this also to the temperature bounds on the house. So let's say you're comfortable, I don't know Celsius, but like 68 to 72 degrees Fahrenheit. And you're okay, if that's satisfied 95% of the time. But if it's really, really beneficial, if you'll save, $3 to go beyond that 5% of the time, you're okay with that. So these are parameters that the user can tune or that can be inferred from those surveys. So here was this red dashed line was the outdoor temperature. We have these thermal comfort bounds you can think of as like the deadband of the HVAC system. The solid blue line is the indoor temperature. We're fine, we're at the top of the deadband. It's hot outside, so the system's keeping it relatively at the top of the deadband. We receive a notice at hour 2 p.m. And the notice says, please reduce your load during this time period. So the 4C system sees this, it pre-cools the house, that's that little dip right here, in accordance with being 95% sure that we're going to be comfortable within the demand response period. And then it turns off the air conditioner, your house naturally heats up, and you're still within the desired range during the DR period. So this just allows for some flexibility in the system. And just for completeness, this is what the main campus of NREL looks like in Golden, Colorado. There's also a Boulder campus, that's the wind site. Here's more of the Smart Power Lab where there's like a clothes washing machine. There's just a bunch of like old white t-shirts that we put in there to add actual load to the clothes washing machine. Here's more. This is literally a panel of different types of LED light bulbs, so people can see the different types of LED light bulbs. And this is like one of 3 test homes in this lab. And hopefully some of you get to go visit NREL someday. There's a lot of really exciting labs there that I was fortunate to work in. Okay, so that's one house. And to be fair, I said all that stuff about, 4C is amazing, it won this award, but it's a little bit unrealistic. Like we're assuming all these devices are communicate. Don't tell my old boss I said that. All these devices are communicating with each other. You have models for all these devices. The utility can somehow, communicate in this two-way stream with you. So let's abstract this away to the neighborhood level, and let's deal with a slightly more realistic scenario. Okay, the utility probably won't know anything about your preferences. They don't know what devices you have. They don't know how much you care about electricity cost. So if I was a utility or an aggregator, how do I know how to elicit demand response, assuming I'm not going to do what my utility does and come out and install physical switches on all my compressors? Can we learn what price to send down to get the desired response? So this is a work that we just started like 3 months ago with my student Ash. And she was looking at, can we use reinforcement learning to determine what price to send to a smart community? So each one of these homes in the community, we assume, and it doesn't have to be, it could be a dumb home. They could all have their own model predictive controllers, something like 4C or just like a standard model predictive controller. The only thing the utility sees, meaning the reinforcement agent, is they see the aggregate consumption of the community. This is what they can see now, especially if you have smart meters, they can actually see individual home consumption. So the RL agent sees, oh, the whole community is consuming, 100 kilowatt hours right now. They can't tell what's going on inside these homes. This is a little bit more realistic. So if you're not familiar with reinforcement learning, it's a different type of machine learning other than the standard supervised or unsupervised learning. The agent interacts with an environment, a noisy, uncertain environment, in this case, this neighborhood. We have uncertainty in solar irradiance. We have uncertainty in outdoor air temperature. We have uncertainty from how many houses there are, what the houses are doing. The RL agent interacts with the environment, and then it observes a response, and it learns from that response. That's what reinforcement learning is. It's a very useful technique because it can be model free. So I don't have to have reduced order models of the homes in here. It can be an online learning algorithm. So I can just plop it in the real system and it'll learn over time. In the beginning, it might make some weird price choices while it's exploring what actions to take, but it will learn over time. And it's been experiencing a resurgence of popularity because of all of these nice benefits of it being realistic. Okay, so we randomly generated a community that had a electric water heater, that had an HVAC system, and some of the houses have rooftop solar. This can obviously be expanded to more devices, but generally everyone's going to have the HVAC system and water heater. So from these parameters, we just had a uniform distribution to select, for example, the R and C values of the linear model that we use to represent the houses. And by the way, this is at the house level. The utility can't see what's going on here. We're just creating the communities. Each house optimizes its own model predictive controller, does not communicate with the utility at all. We randomly generate how their indoor temperature, the bounds at which their indoor temperature is allowed to vary, the size of their water heater, et cetera, just to add more realistic characteristics to the community. Okay, so the utility side, the objective is to flatten the load, to reduce the peak. We generally want to minimize peaks on the grid because we want to minimize the use of peaker plants. We want to defer when we're supposed to upgrade infrastructure, which is often driven by peak load. And we want to generally keep the load as flat as possible. It's more predictable. Generators don't have to turn on and off throughout the day. At the home side, their goal is to simply minimize their bill. We didn't do anything fancy here with pricing comfort or pricing carbon. This is just a more simple, realistic, they want a small electricity bill. The algorithm that we used for reinforcement learning, and I don't have time to go into all the details, but we used a deep Q-learning algorithm, which is essentially, so a lot of the field of AI and even reinforcement learning was driven by robotics and the computer science fields. So in robotics, you might have a discrete action space and a discrete state space. The robotic arm is in this position and it can move left or right. In this particular example, we have a continuous state space. The aggregate load in the community can be 0.00, it could be 0.001, it could be 24.796. So we have a continuous state space. We use a neural network to approximate that and to approximate what action we should choose from, given which state we're in. We had a bunch of other interesting features that Ash did to make this algorithm even more robust. If you're interested, we can send you the paper. Constrained reinforcement learning we're not doing here. The only constraint is on the action space, which says that we can only change the electricity price by plus or minus 2 cents. So one of the big goals here is to have a very minimal impact on the homeowner. On the home side, we have hard temperature bounds, hard deadband bounds for the water heater, models for the appliances. We're assuming they're not allowing any sort of deviation from what makes them comfortable here. Okay, how did it do? So here's over the 30-day testing period. Here's what the average load looked like. So you can see, let's look at the time of use price one first. So with the time of use, that tiered structured price, we have the model predictive control home seeing that the price is going to increase. So they preheat the home, or they preheat the water heater, or pre-cool the home, for example. They don't consume as much electricity during the high price period, and this repeats. These kind of high peaks are what's already happening in communities with high response rates and time of use pricing. All the homes are going to see that price. They're all going to perform that pre-cooling, preheating, or pre-charging the battery, and they're all going to reduce their consumption during the high price period. This isn't always the most ideal situation for the grid, having these peaks. The baseline just means, status quo, flat price. The HEMs are optimizing across the horizon, just given a flat price. And that is this solid line right here. You can see it's relatively flat, still has peaks throughout the day. This is averaged again throughout the 30-day simulation period. The time of use price, you can see it's a little bit squished compared to the baseline price. We have peaks that are less high. We have larger minimums. So the spread, or the distance between the maximum and minimum, is smaller. And in fact, we see an average of almost an 8% reduction in spread. Again, this is good for the utility, keeping the load as flat and as consistent as possible. We get a 3.4 average reduction in peak load, which is also good. You can read about studies where we can save $3 billion by reducing the peak load by 5%. So this doesn't seem like a huge number. If you read a paper and you're like, oh, 3% reduction, is that significant? It's a couple $2 billion significant. So if you find that significant, I guess it is. Also, keep in mind that this is done without inconveniencing the users at all. We have these hard bounds. We're simply slightly changing the way we work within those dead bands. So you can see the numbers here of the average peak demand and average daily spread. Okay, I know I need to talk a little bit faster. Oh, here's just a plot of the fact that we stay inside the dead bands for indoor temperature and for water heater temperature. Another interesting thing to note, so here's the GHI, which would be linked to the solar production in the community. This dashed or dotted line is the time of use price, which is like a standard time of use price that peaks in the evenings to disincentivize people from using electricity then. This dashed line is the reinforcement learning agent price, the one that it decided was the best price, and it learned over time is the best price to elicit this flat response. You can see that it dips during times of high renewable production. And this makes sense. If the community is being self-sufficient, you don't want to charge them a ton of electricity because you want to incentivize them consuming more during that time to keep the overall grid load flat. So this wasn't input to the RL agent. It just learns these patterns over time. It was simply just plopped in there. And then the last thing I'll mention is that we've also used this as, just a test case for transfer learning. So we trained it on one community, and then we plopped this agent in another community with more houses and more solar, and it still reduced the peak load by 1%, for a small testing period. So this is really, really nice because we could just have one community as a guinea pig, as like a warm start for the RL agent before we put it into other communities to roughly learn, load patterns and roughly learn solar patterns. Okay, so the last one I'm going to talk about is at a larger scale. Let's look at a whole microgrid or district energy system. And this is a project that is again funded by the US Department of Energy. It's a $4 million project, so it has a bunch of partners, 2 national labs, a couple universities, and this is a technology company. And so this project seeks to do multiple things, one of which is to co-design microgrid and district energy systems. Another one of which is to develop realistic models and open source these models of these coupled 2 systems. And the third one is to optimize both the design and the operation of these systems. So we're going to use 2 main tools in this project, one of which is Modelica, and that is this object-oriented modeling language for complex dynamical systems. You can simulate on sub-second levels with Modelica. It's it can get very detailed. You can also export reduced order models if you want. We're also going to use something that was developed out of NREL, UrbanOpt, which is a district and campus scale analysis tool. So it uses OpenStudio and Energy Plus as a backend, which are building simulation and modeling tools. And using these 2 tools, we're going to develop this integrated framework that optimizes over CHPs, microgrids, coupled thermal and electrical systems. So obviously, you're thinking, wow, controlling complex dynamical models on a sub-second basis sounds extremely challenging. How on earth would you form an optimization problem that can do that? And that's why I chose to talk about the reinforcement learning project right before this. We're going to use this model-free online learning approach to address such a problem, where we don't necessarily know all the pieces offline. We need to optimize or determine set points in real time, and we don't want to have to deal with 5,000 complex dynamical equations. So that's the general concept. It just started last month, so we haven't gotten too far into this. But the idea is that instead of just designing a microgrid and assuming, oh, there's a CHP in the microgrid, it has this output, or instead of designing a thermal district system and assuming, oh, there's some electrical load, it does this. We're actually combining the design and operation of these 2, including dynamical models, including models of demand, including controllers. And we can achieve, and this is just some preliminary work done by one of the former students at CU Boulder, we can achieve faster and more accurate response rates when we have coupled systems that we're controlling versus conventional separate systems. So this is just attempting to reach a set point. And you can see the coupled system reaches that set point faster. This is a short or small picture of what Modelica looks like if you haven't seen it before. It's kind of like a Simulink, like a block-based language. You can click inside of this and it'll bring you more detail into that particular component. You can embed Python or MATLAB code in Modelica, so you can code these differential equations or whatever you want to put in there in a Modelica block. You can simulate it on any sort of time scale down to like 200 milliseconds or something like that. It is not free. There are free versions of Modelica, like Open Modelica, but we're going to make open sourced versions of these models in the project. And then another big part, which is going to be done in the last year of the project, is we're going to demonstrate the efficacy of this of these controllers on actual microgrids and district energy systems. So there's 2 that we're going to test on. The one on our campus, here's this really nice mock-up model of the district energy plant at CU Boulder. There's also a microgrid and district energy system in the UT Austin campus. And we're essentially, within what facilities management allows us to do, going to change set points and change valve positions and simulate different loading on the system to see if we can really make an impact on a physical system. And this is different than, the simulation test bed that's just computational, because we don't have exact models for all these things. We have a lot of uncertainty. There's a lot of things that occur in a physical system that you don't expect. Maybe things don't react immediately or your models are off. So this physical demonstration part is an important part of the project. Okay, so takeaways from my talk. I could talk for 12 hours about what my group does. I had to pick a couple that was relevant for whole energy systems. But the coordination of buildings can really help the grid. And the coordination of buildings doesn't have to be something that's extremely fancy. It can be, that can improve the user experience, but it doesn't have to be. Buildings can help with grid goals by just buying a Nest thermostat and having it be price responsive. Utilities can design dynamic prices that are only plus or minus 2 cents of what the homeowner expects and still elicit some flexibility to help the grid. And overall, by integrating these systems more tightly and more seamlessly, we can help alleviate a lot of the problems that exist with, peak load or with instability or with sustainability. And so, crossing these boundaries between thermostat and transmission is a big challenge in research and something we're going to have to do very, very quickly. Okay, thank you. I really appreciate your attention. And I'll be happy to take any questions.
Thanks. That was super interesting. I'm sure there'll be lots of questions. Either you can put them in the chat and I'll read them out, or you can raise your hand and you can ask in person. So we got a question sort of I think it was just towards the end of the second part from Flora Charbonnier. Are different prices sent to different customers? And if so, is it acceptable in terms of fairness and market transparency?
Excellent question. No, the price, I should have mentioned this, it's one of the big benefits of the method. The price that's sent to the community is sent to everyone. So it's easy to get a really good desired aggregate response if you're individually tailoring prices, but as you said, this is not fair. So we wanted to see how can we receive any benefit by just sending exactly the same price to everybody.
Cool. It was interesting to hear how because obviously things in the UK are quite different from things in the US. In the UK, everyone has a gas boiler for the most part. There isn't really any AC at all. But there are still a lot of it. So in the UK, there's a retailer called Octopus that has I don't know if they're sort of the most innovative retailer, probably I would say in the UK. They've got a time of use, sort of a dynamic time of use tariff that's been introduced. And that's obviously the same for everyone, except at the sort of very large scale. It's only sort of within the the different sort of a couple of million people per network. Got a question here from Chris Mullen. Can you say a bit more about the models you are developing in Modelica? Are these just plant or controllers as well?
So I'm not doing the model development part, but from what I understand of the project, we're going to be developing coupled models. So there already exists CHP models in Modelica and microgrid models. And part of the RPI team was one of the leaders on the power grid part in Modelica. CU Boulder, Wang Dezuo, who's the PI of this project, is one of the leaders of the buildings library in Modelica. So we're going to be using all of those existing tools, but developing interfaces to connect them. So the Modelica models that are going to be developed are sort of the thermal electrical interfaces, as well as reduced order models that can be used in different controllers that we're going to compare. And then, yeah, I wanted to mention about the dynamic pricing. So the only area I'm aware of that has real-time dynamic pricing in the US is Chicago. And the price actually reflects the LMP and it changes every hour. The locational marginal price changes every hour. They read it in they calculate it every 15 minutes, but then the consumer gets the averaged hourly price. And there was a study done, I think 5 years ago, that said consumers actually ended up paying more under this model because a lot of them don't have automatic devices that respond. So it relies on them to, hourly schedule, which isn't realistic.
Yeah, because it's always one of those things, the keen beans come along and they sort of, they sign up for these tariffs and they can do everything. And then you give it to the person who's not so interested, then exactly. Sort of can't do quite so much. Question from Neil Wade here. Presumably the DR action caused an increase in cost, which is offset by a payment. Do you record how much the increase in costs are before they are offset by a DR participation payment?
Yeah, that's an excellent question. So what we did in this work was the RL agent has a base price for which it adds plus or minus 2 cents. It doesn't affect the response of the homes because their objective function is in relative terms. So what you can do to achieve a similar cost for the consumers, you can just tune this baseline price up or down to ensure that the consumers don't end up paying a lot more. We did it a little bit offline, didn't really end up in the paper, but that's how you would fix a problem like that.
Cool. And the next one here from Liang Han. For RL, reinforcement learning, to work, I'm assuming that everyone has to have their own optimization controller of all home appliances, right? And when you talked about 3% peak shaving, is that comparing to the scenario with time of use pricing or flat pricing?
Yeah, everyone has to have some kind of controller to work. That's accurate. And it needs to be price responsive. So if you had a whole community that was just normal consumers, nothing price responsive, the RL obviously wouldn't do anything. It would just learn that, oh, nothing is happening, so I can pick arbitrary prices. So yeah, there needs to be a simple controller. This could be something like we have Nest that has this rush hour rewards program that directly communicates with the utility, reads in the price, and pre-cools or preheats your house. Something as simple as that could work. You don't necessarily need water heating or like battery or PV in there. It would reduce the performance, of course. And then the 3% peak shaving was with respect to the baseline. So the amount that it reduces the peak from the time of use is much more significant, but I think it's more fair to compare it to a flat rate rather than the worst case scenario.
Cool. I'll jump in with another question while we see if there's any more. So one of the things which I find quite interesting at the moment, some of your colleagues at NREL have got these projects where they sort of modeling these enormous distribution networks. There's this, what is it, the whole San Francisco Bay Area, they've sort of got this synthetic model that they've created. What do you think is the best scale? Because my sort of understanding is that that's kind of a fun project, perhaps, and it's sort of something that people can explore and play around with, but obviously that's a long way from what is sort of in practice used. At what scale do you think sort of aggregation is going to be most useful? Because obviously you've sort of talked about 3 scales here, this sort of microgrid, a couple of sort of small community and then individual buildings. But where do you think the sweet spot is? Do you think we should be modeling these enormous areas or sort of somewhere in between?
I think the benefit with that, just to give them the benefit of the doubt, is if you're doing something like voltage regulation plus like peak shaving or load shifting, then you really need the scale of distribution feeder up to citywide. I had a project while I was at NREL with a couple California utilities, and it was individual distribution feeder models. And they were like, if everybody buys solar, we're going to have a huge problem, right? Can you tell us like what it's going to do to the voltage? So a lot of those like locational constraints like voltage, I think you need that detail. And then abstracting it away for like, yeah, larger level grid services or determining if there's enough generation capacity. I think that's sort of what they're going for there with those models. But yeah, I've heard about the project, but I haven't looked into it totally. But yeah.
Cool. Are there any more questions? Again, you can raise a hand and I'm happy to read them out if you put them in the chat. I guess one of the, Liang's just asked another question. With the model predictive control, how do you model people's flexibility with the thermostats with the threshold on the amount of savings, as you mentioned in the first example?
So the flexibility in the thermostats is sort of this deadband parameter. That's sort of like, you know, how much can we play within the deadband? Because traditionally, yeah, you probably know it's like hysteresis, bang, bang control. It gets too cold, you turn on the heater. Gets too hot, you turn off the heater. You know, it just goes up and down like this. But we can change those patterns, and there's still some inherent flexibility in there. If you have a tighter deadband, then obviously you're not going to be able to shift load as much. But if we integrated something like batteries into this, I think it would really improve the ability of the homes to save money.
Cool. And a follow up again here from Neil.
Is it okay if I clarify?
Oh, sorry, yeah, carry on.
Yeah,
yeah. So what I was meaning to ask was when you mentioned it I think in the first example, when you were just asking people to, give their preferences on how they control their thermostats, and sometimes they can relax their thermostats a little bit depending on the savings. So that's kind of my question. When you're actually doing the model predictive control, do you still take into account that extra level of flexibility?
Yeah, I'm trying to remember now. This is in 2015. I think, or this started. I forget exactly how the preferences are translated into weights. It's something by relative, like it's pairwise comparison. And it's somehow like the relative ranking somehow translates into a number. There's also hard bounds. So let's say you ranked shower temperature number 1. The user can also input like, I refuse to ever have a shower that's too cold. And you can put hard bounds on all of these things and it'll just optimize for comfort as one of the 4 C's. Now, if you're putting saving money at the top, but you also put hard bounds on everything, the hard bounds are still going to override the preferences that you ranked here. And we did some surveys on Amazon Mechanical Turk with I think 1,000 people. And a lot of them said they cared about environmental impact, but I bet when this actually gets put into people's homes, there's going to be less caring about environmental impact and more caring about having a hot shower. So it's hard to say whether or not this would even be an accurate representation because people don't know what they want all the time.
Yeah, and is that taken into account in the model predictive control as well? How? Okay, yeah.
Not yet, actually.
Okay, yeah.
So one of these inputs, the user preferences, those are taken to be true. There's uncertainty in other parts, but not in the user preferences. Yeah.
Right,
not yet.
Okay. All right. Thank you.
Thank you.
Okay, I'll go on to, as I say, Neil's got a follow-up. How long before this is commonplace? I don't know exactly what this is, perhaps the session, rather than being driven by research projects.
Yeah, so that's a good question. And that's one of the frustrations. Actually, that's the reason why I went from transmission level research only down to building level research, was because, yeah, we put this in a couple people's houses. The ones that are in people's houses only control the HVAC set point right now, but it's much easier to create these modular devices that people can volunteer to be living laboratories for, if you will. This part, the determining the prices. So apparently utilities and aggregators already use, artificial intelligence to determine time of use prices and to determine these real-time prices in areas that have those. The, AI is mostly just like linear regression. Like, what did people do in response to this price? Let's change the price to be this, plus some human in the loop. So this is kind of happening. You could plop this inside of an aggregator and try it. That's something that probably I could pursue if I, really bugged the aggregator here. But yeah, I don't know how complicated what's going on inside these is right now. But I would say it's within the realm of feasibility now.
Cool, yeah, and in the UK, they're developing a standard actually at the moment that is supposed to be demand-side response for appliances, and it's sort of going through various bits and pieces at the moment. I think they've got a sort of public consultation, and it will come in sort of a couple of months. So it feels like it's something that is coming. I don't know that it's there yet, but
yeah, we have standards that are recommended IEEE standards for if you have frequency response, or if you have load shifting, what's the time that it has to respond, what information does it need, what kind of communication protocol does it use. I think those practical considerations, especially for the 4C project, are probably more of the roadblock than anything. Something like this is a little bit more realistic because, yeah, it's easy for people in ComEd in Chicago to just change that price in real time. as long as it's, plus or minus 2 cents, like I said.
Yeah. Cool. I got a question from Ifu Ding. Thanks very much for the excellent talk. How could the microgrid respond to a blackout? Does it consider this within the current model?
Yeah, that's a great question. Part of what motivated this was the PI was looking at a small community in Florida, which is really prone to hurricanes and power outages. And they were looking at how can we create a real microgrid for this community in Florida. And so a lot of that knowledge is going to be embedded in here, and we're going to simulate scenarios like, oh, there's a grid outage. Can we provide power for 72 hours? Because the biggest part of this is not the control, it's actually the design. So we should determine what size of battery do we need, how flexible do the loads have to be, a lot of resiliency considerations, because that's one of the big benefits of a microgrid, I would say, in a district energy system.
Cool. You said this one has got a CHP unit in it, so it can.
Yeah, we have a CHP unit on our campus, and there's one on the UT Austin campus. Actually, there's 2 on our campus, but I think we're just using 1, maybe 2. There's a CHP that's pretty old, and then there's active efforts to build out the microgrid. So they're putting in more batteries and more solar panels, I think, now in the CU campus.
Cool. Yeah, microgrids are interesting, I guess. It's interesting that's because in CU, within Colorado, would it be like a sort of snowstorm kind of scenario? Because obviously in Florida, I guess you have these sort of hurricanes is the big thing. Is it sort of snowstormy type events you'd be worried about, I guess?
The biggest one that's caused blackouts in Colorado in general is wildfires. We have multiple wildfires going on right now. Unfortunately, they've destroyed thousands of acres, caused power outages in huge areas. Oh, hold on, my computer says it's going to restart, and make sure it doesn't do that. Okay. And so wildfires are actually the big risk, and those are getting worse every year because it's just so hot and dry here, and there's so many wooded areas that have, like, not branches, but like old branches everywhere that can easily start fires. And there's also a lot of people that camp and don't put out their fires properly. The snowstorms do take down lines. In Boulder, the utility has this big plan of like hardening all the lines, so replacing all the poles with more reinforced poles. But generally, Colorado is prepared for snow, but not prepared for wildfires. So it's more on the summer side.
Interesting. Fair enough. Yeah, I guess we're coming towards the end. Before we thank Kyri, I'll just two quick messages. So firstly, in 2 weeks' time, we've got our next speaker will be Graham Hawker from Strathclyde University. He'll be talking about drivers and challenges for multi-energy systems analysis. Graham's worked in the energy industry for many years, and he's recently done his PhD as a researcher. Really fantastic researcher, so do come along to that. Secondly, if you have any feedback, we're hoping to run this series again next term. We've had a really positive response. So if there's any particular part of whole energy systems you think that we're missing or you'd like to see more speakers on, do get in contact with myself, David, or Chris. And with that, many thanks to Kyri. And if you'll clap, or I don't know, I'm still yet to work out the best way to end these things. Say thanks very much.
Thank you.
See you all soon.
Thanks very much.
Thank you.
Yeah.
Thank you.